The concept of system of imprimitivity is used in mathematics, particularly in algebra and analysis, both within the context of the theory of group representations. It was used by George Mackey as the basis for his theory of induced unitary representations of locally compact groups. The simplest case, and the context in which the idea was first noticed, is that of finite groups. Consider a group G and subgroups H and K, with K contained in H. Then the left cosets of H and G are each the union of left cosets of K. Not only that, but translation by any element G of G respects this decomposition. The connection with induced representations is that the permutation representation on cosets is the special case of induced representation, in which a representation is induced from a trivial representation. The structure, combinatorial in this case, respected by translation shows that either K is a maximal subgroup of G, or there is a system of imprimitivity. In order to generalize this to other cases, the concept is re-expressed, first in terms of functions on G constant on K-cosets, and then in terms of projection operators. Mackey also used the idea for his explication of quantization theory based on preservation of relativity groups acting on configuration space. This generalized work of Eugene Wiener and others, and is often considered to be one of the pioneering ideas in canonical quantization. To motivate the general definitions, we first formulate a definition in the case of finite groups, and their representations on finite-dimensional vector spaces. If the action of G on the elements of X is transitive, then we say this is a transitive system of imprimitivity, such that G0 is the fixed-point subgroup of W under the action of G, i.e. and V is equivalent to the representation of G0 on W0 given by a bar W0 for HA circumflex G0. Note that by this definition, induced by is a relation between representations. We would like to show that there is actually a mapping on representations which corresponds to this relation. Thus the character function I umlaut U is completely determined by I umlaut V. To generalize the finite-dimensional definition given in the preceding section, a suitable replacement for the set X of vector subspaces of H which is permuted by the representation U is needed. As it turns out, a René Macron V approach based on subspaces of H will not work. For example, the translation representation of R on L2 has no system of imprimitivity in this sense. The right formulation of direct sum decomposition is formulated in terms of projection-valued measures. We will refer to this as a standard Borel G space. The definitions can be given in a much more general context, but the original setup used by Mackey is still quite general and requires fewer technicalities. For all G circumflex G in Borel subsets A of G, then is a system of imprimitivity of on L to I circumflex 1/4. This system of imprimitivity is sometimes called the Koopman system of imprimitivity. A system of imprimitivity is homogeneous of multiplicity n, where 1 circumflex symbol n circumflex symbol I umlaut, if and only if the corresponding projection-valued measure I umlaut on X is homogeneous of multiplicity n. In fact, X breaks up into a countable disjoint family Xn1 circumflex symbol n circumflex symbol I umlaut of Borel sets such that I umlaut is homogeneous of multiplicity n on Xn. It is also easy to show Xn is G invariant. Lemma. Any system of imprimitivity is an orthogonal direct sum of homogeneous ones. It can be shown that if the action of G on X is transitive, then any system of imprimitivity on X is homogeneous. More generally, if the action of G on X is ergodic, then any system of imprimitivity on X is homogeneous. We now discuss how the structure of homogeneous systems of imprimitivity can be expressed in a form which generalizes the Koopman representation given in the example above. Conversely, any homogeneous system of imprimitivity is of this form, for some measure I umlaut dash finite measure I circumflex 1/4. This measure is unique up to measure equivalence, that is to say, Two such measures have the same sets of measures 0,